All right, so last Friday we talked about forces, right? Okay. What is a force? Push or pull. What's the equation for a force? F equals m times a. Okay. We talked about a way to diagram forces. What was that way? What was it called? Free body diagram, or FBD. Okay? FBD, or free body diagram. Now look, here's a scenario. Let's say I've got some sort of funky object, okay, and it's got a bunch of stuff on it, right? Okay, who cares what the object is? Bacteria with a bunch of stuff on it. It's got a force on it. It's got a force on it. It's got a force on it. It's got another force on it. Okay? Everyone draw, I'm going to call this F1, F2, F3, F4. Okay? All right, if I'm going to do a free body diagram, I can draw the free body diagram as a circle or a square. Doesn't matter. Something simple. A very simple representation of the object. Then I'm going to draw all the forces. F4. Notice I'm drawing it at the angle. F2, F1, and F3. And I'll deal with this in a minute because you typically will not have angled forces on here, but for the start, you can start here. So this is just showing you all the different forces on that body. This is a free body diagram. Everyone clear on that? Yub yub? Yub yub. Okay. This F3, let's assume F1 and F2 are vertical. F1 and F4 are vertical. What about F2 and F3? Are they vertical or not? Are they horizontal, vertical? What are they? They're a combo. So what do we know about forces in the vertical and horizontal direction? Well, let me tell you, what do we know about motion in the horizontal and vertical direction? They're what? Independent, right? Okay. But motion comes from what? A force, right? You've got to have a force to give you some motion. So what does that mean about the forces in X and Y? They're what? The horizontal forces and vertical forces, they are independent, okay? But because we have this F3 at an angle, we have to do what with it?
Break it down.
Okay, break it down to components. So you can break this down to F3X
F3Y.
and F3Y, okay? Okay, but wait a minute. If I put F3X and F3Y on here, is it appropriate still to have F3 on here? If I'm drawing all the forces on here, what does F3X plus F3Y equal? F3. Right, because now this is showing me that I have two F3 forces. I've got F3 at the angle, but I also have the components, which means I'm doing it twice. Does that make sense? And you don't want to do that. So you want to take F3 and do that. Does that make sense, Sean? That's the inquisitiveness? The eyebrows. All right, we good? See why I'm doing that? Because at the end of the day, what were we doing on Friday with these forces? What were we doing with them?
Right.
What were we?
Net forces?
Yeah, what do you mean net forces? How did we get a net force? We're summing the forces. But if we're summing the forces, I can't sum the original F3 and the original F2, can I? No. I can sum the X's and the Y. Some of the forces in the X and some of the forces in the Y, right? Does that make sense? You got to break them down. So F2, what am I doing with F2? Same thing. So I'm going to make a F2Y and an F2X. And then I have to do what with my F2? Get rid of it. Okay? So when I talk about a free body diagram, I really mean an orthogonal. Orthogonal, everyone knows the word orthogonal, perpendicular, X and Y forces. Is that clear? That's my FBD. And then I'm going to sum all the F's and the X. What are the forces in the X? F3X, okay. I can't seem to write today. 3x. What are the forces in the y? F1. Okay. So notice that F4 is positive, F2y, F3y, and F1 are all negative. But notice I just added them anyway, right? Just a sum, the signs will come in when you put the values in, okay? I like you guys, especially here in honors, I want you guys to work equation variable down. So put your equations with your variables and then get them down to that point. And then when you've got all the variables set in there, then you can lay in your numbers, okay? As much as you can work with the variables, the better. I promise you. It'll actually work out better if you can do your variables as long as you can. So you've got these two summations, right? And what is this sum of the force and the x going to equal to? What's it going to equal to? It's my net force, right? Which is equal to my mass times my net acceleration in the x. This is the net force in the x. Sum of the forces net in the y equals mass times acceleration net in the y. Now, these are just my notations, okay? But you need to understand that you've got motion, acceleration, okay, both in the x and the y. Because at the end of the day, when I'm all done, I might have motion, I might have motion off at an angle, couldn't I? Right? Okay. Everyone clear on this? This is sort of a high-level example. Yes, sir?
I'm a little confused by what you mean at the end, like of the like forcing x and x.
This one?
Yeah.
The net. So if I'm saying I get F2 and F3, right? Mm-hmm. If F2x and F3x are the same values but opposite, I'm going to end up with a net force of 0.
Yeah.
Okay? However, if F3 is bigger than F2, I'm going to be left over with some sort of force.
Yeah.
Which means I'll have what? What kind of movement? What kind of movement if I have the... Huh? What kind of movement? Am I going to have constant velocity or constant acceleration? Okay, let's deal with this. No, wrong.
Constant acceleration.
Okay, if I'm going to be left with a force, and let's say I'm left with some... Right. If I'm left over with the value, right, it's the mass times some acceleration. If my let's say these are equal and opposite, I'm going to get some of the forces equaling 0. Which of these values is 0, A or M? Can I have 0 mass? No. I mean, if I've got an object that had mass before, assuming that I didn't have a collision and break things apart, my mass is still going to be there, but my acceleration is going to be 0. Okay? But if I have a net force of some value, positive or negative, I'm going to have some acceleration, positive or negative.
Yep.
Oh.
You follow me?
If the net is something.
If the net is some non-zero number, it means my acceleration is going to be non-zero. Right? Which means I'm going to have accelerated movement. Am I going to have constant velocity movement? With a positive, with some sort of value of f, some sort of non-zero value, am I going to have a constant velocity? Why not?
Because the force is there and keep.
Give me a better reasoning. Talk about
speeds up.
why.
Because of the acceleration.
You have acceleration, and the definition of acceleration means that I have what kind of velocity?
Increasing.
Not necessarily, doesn't have to be increasing,
Changing.
just a changing velocity, right? The fact that I have a value for acceleration means I'm changing my velocity, right? Okay. All right, let me ask you a question. Let's say I have, okay. Okay, this is from Tasmania. Okay, is it crate? If it's from Tasmania, what's in it?
The devil.
Tasmania. All right, good. My first period class doesn't watch cartoons or something. Don't get that. All right. So got a rope carrying this Tasmanian crate off the ship. Okay. Let's say it's in the middle of the air. What kind of forces do I have on it?
Gravity.
Okay, I got my force of gravity. What else do I have?
If there's any movement on the rope, it's swing, I guess.
Huh? Well, let's assume right now it's just
What's longer? A rope?
what? You might have, if you had wind, we might have wind force. But let's say it's moving purely in the vertical direction. No wind force. What's my other force I have? Pull of the rope, right? We have the pull of the rope. And we're going to call that F of T. T being tension. Now, unlike the conversation this morning, we don't mean stress, like he's stressed out. Now, stress is an actual material piece. What now?
He's in a box, he's probably
He might be stressed. But we talk about tension. What do we mean by tension? I'm gonna take a sidetrack for a moment. What do we mean by tension?
the rope has to hold up the box, so it's like, so the rope is
Okay, so what? Oh, okay. Very good definition. Shh. Nicely done, Colby. We have a force on each side. And if the rope isn't moving, the force on this side must be what to the force on this side? Equal. So something is in tension when something's pulling on it. What's the opposite of tension? Compression. Okay? That means my forces are doing what? Going what direction? Sean? Inward. Okay? This is the force of compression. So rope works in how many directions? Tension and compression? Does a rope work in compression? No. What happens when you try and push a rope? Yeah, it falls apart. It kind of slacks out. Okay? Buckles. It's called buckling. So rope and loose wire or flexible wire only works in tension. Okay? So when you think about a tension bridge or a suspension bridge, they're made of these wires that have to be in tension. Okay? But I can have columns, which are typically more solid material. They can work in both compression and tension. And you use these, let's look at, this is a good example up here. If you look at this beam set up here, right, you've got these sort of angles here. Those three, we've got, if I'm looking at those beams here, I've got a beam, I've got this beam, right? And I've got like a beam here, and I got a beam here, and I have a beam like here, right? Okay. Now the question is, what are those beams in? Tension or compression?
Yeah. Right? They wouldn't be pushing up.
Okay. This comes to an engineering question, and you have to start to do a lot of the force
Good thing
calculations.
we're not in that.
Huh? Well, okay. At the end of the day, you don't know. Okay? You have to do the math. Okay? Depending on the load and the position of the load, these beams may be in either compression or tension. By the way, that's why they're solid beams and not ropes. Like if I knew, let's say this was a force of compression and this is a force of compression. If those are compressing, that means it's trying to push this down. Well, if this is attached up top, what happens to this member? It gets pulled. It's in tension. Okay? But if the wind load changes and I give a different force here and I get other things, that might actually be into compression. So the reason they don't use wire in those cases is that beam, in some cases, may have to do a dual position. It might be a compressive or tensive, depending on the loads and the dynamics of it. So when you see these bridges that are made up of, like, you've seen them, I'm sure you've all seen these bridges that are like this, right? And you see them like this, and you've got that and that kind of thing, right?
Yeah.
There's mathematics around how to figure out which member is in tension or compression at what time, depending on the load. If my load is here versus my load here, these members might be in tension in one position and compression in the other. That's why they choose, because if it was always in tension, it's cheaper just to make a cable, right? But because you need the compression factor, you need to use a beam. Okay, so it depends on the scenario. Does that make sense? Okay. All right. So back to our problem for a second. Back to our piece. We call this force of tension, and to Colby's point, if it's tension, then the force on either side is the same. Okay? And that's going to be important when we start to do a couple of things in a minute. But if I've got this, let's draw. I want everyone to draw a free body diagram of this box.
I drew it.
Everyone draw a free body diagram. Everyone to do that. Ah, man.
Yeah, I've done it.
Everyone should do that right now. Okay, everyone have that? So your free body diagram should look something like this. Okay. Now, that's your main body. I don't go through the whole graphics. It's just a square or a circle. Doesn't matter. Where are my forces? Show me what. Does anyone have it like this, where I have F of G, and what's my other force? F of T. Who has that? Raise your hand if you have that. Raise your hand if you don't have that. You have something different, which is okay. What do you have?
I have the top.
Okay. So you have this. You've got F of G going this direction, right? And F of T going this direction, right? But the arrows are up and down, the correct orientation. Is there anything wrong with that? No. Technically, it's correct. Now, it's not as intuitive as the other way. But there's nothing wrong with this. Perfectly acceptable. As long as your arrows are the right direction and you're labeling them correctly, it doesn't matter. Does that make sense? I could have also done this. Right? As equally as correct. Not as intuitive, but equally as correct. Right? Make sense? Okay. So that's the scenario. So let's say for this scenario, now everyone write an equation. If you guys, I'm going to redraw this. Everyone write an equation for the sum of the forces in the y. Everyone write an equation for the sum of the forces in the y. Okay, what do we have? Okay. Sum of the forces in the y equals f of g plus f of t. Okay, and that equals what? What does that basically equal?
What? You saying like?
What is this equal? Ultimately, it's a net force, right? Mass times my net acceleration. Okay? Mass times my net acceleration in the y. And you can call it in the y. It's not... do it if it makes sense, right? But acceleration in the y. Does that make sense? Okay, now, let's assume...
Looks like you're a baby.
Yeah, any, right?
That's not good.
That's not right. It's not any. It could be any.
Okay.
Oh.
I'm just gonna leave the y out for the moment. All right. So here's my question. Okay. Let's assume that my force of gravity is negative 100 newtons, and let's assume that my force of tension is positive 100 newtons. What's a negative for? What's a negative and positive do for us? Shows us what? Direction, right? Okay. So now that means that my sum of the forces in the y is equal to what? Negative 100 plus 100 equals 0 newtons, right? Okay. What kind of motion does the box have?
No.
Zero. Rest.
Constant distance.
Constant acceleration.
Constant position.
But
Okay.
Zero.
What? Okay. Okay. Let's be. This is my trick question. Okay. This means that mass times acceleration net equals 0. Was my mass 0? No. So my acceleration is what? 0. That means I have no what? No acceleration.
So it's constant acceleration.
But could it have velocity? Don't know. So saying that it has no motion is incorrect.
Was I right when I said constant acceleration?
technically yes, of zero, but you have to clarify that with zero. You have to say constant acceleration of zero, which you didn't say.
I said that after.
Oh, did you? Okay. But the issue, what the type of motion you really have is a non-zero or a constant, a constant velocity, which the heck is going on? Which could be zero or some sort of number, right? You can have motion and no net force. Does that make sense? Everyone clear on that? Okay. So this is a trick that I think a lot of people sort of make that assumption because I have no acceleration, I have no motion. Incorrect. You don't know that yet. Okay? You could have a constant velocity of zero or a non-zero constant velocity. An elevator is a perfect example. When you get in the elevator, you feel a bump, right? You might feel, if you're going down, you might feel a little weightlessness. If you go up, you might feel a little bit of compression. But at a certain point, you feel what? Nothing, right? You close your eyes, if you didn't hear anything, you wouldn't know what's going on. You wouldn't know you're moving because you have a constant velocity. The only reason you know you're moving, Trip and Tino, is that you feel the acceleration. If you're in the car, cruise control, close your eyes, you have no idea whether you're moving or not, except for the rumbling, right?
I've never closed my
Don't do it while you're driving, while you're being the passenger. Okay, cool. Everyone clear on this? Okay. Now, let's do one other thing. I'm getting a little messy here, so I'm gonna try and clean up. Shoot. The heck? Oh, that's what I'm doing. Okay. Let's assume, guys. Let's assume this. I'm gonna move this guy over here. Move him out of the way. Shrink him down. There we are. Okay. All right. Now. Okay. Let's assume. Let's change it up a little bit. Let's assume. I'm gonna move this out of the way. Let's assume all of a sudden that I have this crate on the ground. Okay? Let's assume that that's 0 newtons. Let's change it up. Let's do it this way, so we know. Let's make it 80 newtons. Okay? So now, if I do my summation and I change this up, right? So it's negative 100 newtons plus 80 newtons. What am I left over with? What am I left with? Negative 20 newtons. Well, what does that mean that I'm left with 20 newtons? Okay, you might say you're going down, but the crate's on the ground.
Pressing down the ground has a weight to it.
It has a weight to it of how much? Well, it has a weight of 100 newtons, but it's
being lessened by the rope by 80.
well, the weight isn't being lessened. Okay, let me combine Michael and Daniel. Michael, you said you're pushing on the ground or compressing the ground. Daniel, you said there's a what?
A force coming
from the ground responding, right? There is a force. We called this the force of table or reaction on Friday. I'm going to call it the real force, which is called the normal force. What is the geometric definition of normal? Anyone? Not when I say normal, it doesn't mean that we're not talking about David and we're talking. Whoa, that's fighting words. No, we're saying. I know. Oh my God. So we're not talking about normal, abnormal. What are we talking? What's a geometric form? What's a geometric definition of normal?
Isn't it like opposite reciprocal?
I don't.
Like -1 over.
All sides are equal.
I haven't heard that definition. Or if I have, it's been many years. Geometrically, when we talk about normal, we talk about perpendicular. Okay. Remember we were in SolidWorks and we're doing something. We said the normal 2 view.
Normal 2.
Perpendicular. Okay?
Normal 2 is the best one.
So normal is perpendicular. Okay? So that means the force perpendicular coming perpendicular to the floor. Okay? So in this case, there's a reaction force here. So when I look at my summation, it's really f of g plus f of t plus f of n. Okay? All right. I need a volunteer.
Great.
Someone light.
Drew,
Someone small.
not Drew.
Here, use it. Okay. You have to reveal your weight. You okay with that? All right, have this stand up
I'm
there.
pretty sure that scale's like very strong.
Okay, so we've got
114.
What we got?
120. 85. 150.
about 110. Close to 110. Okay? You're gonna see it? Okay. So that's Yusuf's weight, right? Okay, now hold your arms out, go on your feet. You okay with that? Okay, sure. Alright. You can say no. Alright, keep going. Now, watch, Ellie, read the scale. It's 110, right? Now, what's up? What's the reading?
60, 50, 40, 30, 20.
You're still
It's
strong.
0.
Okay, 0. Okay. So, huh?
Do you lift from?
So what's happening? So let's describe what just happened relative to this model. What's happening? Talk about the scale number, Yusuf and me versus this.
Okay, so you're in the rope.
I'm a what?
You're the rope, and the force of the rope is going up because you lift him.
Okay, so I'm lifting positive force of the rope. Yusuf represents what? The crate. What does the number on the scale represent?
How much force is like it's
Gravity.
and it changes.
It's a force coming from the ground, which is called we just called it normal force. Okay? So the force that the ground is pushing back up, perpendicular to the floor on Yusuf is the normal force. That normal force changes depending on how much I'm pulling up on Yusuf. Does that make sense? Because the floors, again, the table's going to support this, it's going to support me, right? Okay, that reaction force is going to change. If Yusuf's on the scale and we lift Yusuf up and we pull just a little bit, if Yusuf weighs 110, I pull 50, what's he going to weigh? 60, right? Okay? And I can continue to do that. But his weight is still 110. The normal force is only 60. The force only has to respond to the amount of weight that is left over after I apply it to him. After I apply upward force against him. Does that make sense? Okay. So the normal force, guys, is an important force. It is going to it's really important to understand what the normal force is. It's important to understand a couple of things. Number one, that it changes depending on how much is being applied, how much force is being applied. Number two, you have to know that force, no matter what, if this is my floor this way, let's say it's a ramp, my normal force is always going to be perpendicular. Okay? All right? Always perpendicular to the it's going to act on the object perpendicular to the surface that it's on. Okay?
What if there's like more weight on one end of the box? You know, if it's like that, all the weight's gonna go to the bottom.
Well, no. All the way.
Like a solid box.
Yeah. I see. You're saying if there's like a bunch of like it's half full of water. Yeah. Then that's a more complex problem. You're right. But let's assume it's a solid box, a uniform weight. Okay. Because then we can assume that from the center we have our force of gravity. Okay. We'll deal with that in a minute. Okay. But the reason normal force is important, guys, it's going to help us deal with friction as well as centripetal force. Yes, sir.
So that Fn on the Tasmanian diagram, that's a force normal?
Yes, that's the normal force. You're gonna see this a lot. You're gonna have to solve for Fn, the normal force. You're gonna have to solve for that. So keep that in mind. All right, does that make sense? So let's say in this case, 80 and 100, then if I know that, then I can solve for my normal force, can't I? All right, plus Fn, okay? And if my box is sitting on the, if my box is sitting on the ground, what should the sum of the forces be? 0 newtons, right? And therefore I can solve for my Fn. If the summation was not 0, say it was a positive number, what does my Fn happen to be? What does that mean? Let's think about that for a second. If, let's say, right, has an acceleration. Acceleration. And therefore, if it's moving up, is it on the ground anymore? How much is the ground pushing back at that point? Well, if the box isn't sitting on the ground, how much is it pushing back at the ground? 0.
Oh, I thought you meant like as you push it up.
No, like once it's moving, yeah. So, in a scenario where I am sitting still, okay, I can solve for f of n, right? F of n is equal to 100 newtons minus 80 newtons. So f of n must equal what? How much?
20 newtons.
And it's positive, isn't it? Is that the right direction? Yes. Okay. Does that make sense? When f of t equals f of g, what is my normal force? 0, right? Does that make sense? Everyone clear on this concept? Okay. What time does class end?
You might say.
1 minute.
35? What is 10? 11:35? No, we have 11:40. Wait, 5 minutes. Okay, good. All right. So let's do this. Let's do a quick problem, okay? Cool? Cool, beans, yeah. All right, so let's say we got our crate. I'm going to draw a very quick crate. Let me come back, actually. Let's do this.
Just draw the.
I'm just going to copy the crate.
That's lame.
Just
I
draw the
know.
FPV. Just draw.
You can't copy and paste our grade.
No, you cannot.
Just draw the FPV.
No, you may not. Okay. All right. Isn't it wonderful? It's so wonderful. Okay, so let's say, okay, let's say I have a force, tension. Let's say I have another rope. Oops. Force tension 1, force tension 2. Okay. I want you to do a couple things. Let's say the box weight, the weight of the box, is 100 newtons. Okay. And let's say F of t ends up being 20 newtons. And let's say FT2 is 30 newtons. And let's say it's at,
Is newtons a weight, like in the box?
well, didn't we talk about that last week? Newtons is a force. Newtons is a force, right? Weight is a force because it's force times acceleration of gravity. The force of gravity is a weight because it's a mass times acceleration of gravity, right? So 30 degrees. So I want you to do two things. I want you to draw me the free body diagram. Draw me a free body diagram. And 2, I want you to solve using start with your top level equations. I want you to solve for the normal force. Go. Draw the free body diagram. There is gravity because I said the weight is 100 newtons. I'm just showing that's exact, and this is because you're saying, Ellie, Mr. A, you didn't draw gravity this time. I didn't. You have to determine that. That's the idea. In the free body diagram, you have to put that down, depending on the information. Weight of box is 100. Ft is 30 newtons at 30 degrees. I don't know why I said N there. And then Ft1 is 20 newtons. So draw the FPV, and then solve for the normal force. And then for extra kicks here, okay, assume that this is frictionless. Assume this is frictionless. So frictionless. What's the motion? What's the motion of the box? Okay, direction and amount. Yell at me if you have no idea where to start. Can everybody do the free body diagram?
Wait, what is number 1 say?
The free body diagram. Draw me the, I'm sorry. What is the, draw me the free body diagram. Solve for f of n. The motion of the box, the direction, and the amount. Ignore the fact that the box is rustling because of the Tasmanian devil inside.
That's a 30 newtons for FT2.
Yes, 30 newtons. All right, finish this for homework. Come back tomorrow.
Yeah.
No.